In this lecture, I'm just going to introduce ANSYS. I'm going to introduce simulations. What is ANSYS? What is a simulation? And basically, we're going to take it from there. Again, this is Engineering-280. We're going to be going through this course for the fall semester. My name is Ali. I'll talk a little bit more about why I'm here and why I am qualified to be talking to you guys. So before I go ahead and talk about that, who is the target audience for this course? And in my opinion, the target audience generally, ideally, should be engineering students or physics students, anybody really who's interested in physics or applying physics, or really anyone who's interested in simulations in general. Again, curious about what are simulations, how to use them, how they help us solve problems, and in general, anybody who likes to have fun learning. So this class is going to be very hands-on, project-based, and we're going to try to relate everything we do to the real world such that it's not going to be boring. It's actually going to be a lot of fun. So prerequisites to taking this course is just mere curiosity, imagination, just being able to visualize things and apply them in software, and ability to take what we're doing here and apply it to the real world, and likewise ability to look at the real world and get inspiration and think of things that you can simulate here, and basic understanding of physics, mechanics, electromagnetics, very simple stuff. We're going to actually go through this stuff very briefly, and again, there's no prior simulation or programming knowledge necessary. We're going to do everything from scratch, which is very nice if you're someone new to this kind of stuff. So again, what are you going to be learning? We're going to set up and run simulations. We're going to, again, talk about what simulations are, how to use ANSYS and other software that are similar, how to think about physics problems, really, because that's really the whole goal of simulation, is to be able to think of physics in an application perspective and relate things to the real world. And hopefully by the end of this course, you'll be able to develop a deeper understanding of mechanics, electromagnetics, and material science as well. So you might be thinking, is this class going to be hard? No, I think the stuff that we're going to use, at least the physics that we're going to be studying and applying, is things that have existed for hundreds of years, mainly mechanics and electromagnetics. And the software that we're using has been around for over 20 years, meaning there's a lot of resources online. There's a lot of people who went ahead and used it and ran into enough issues such that we likely won't have to do any debugging or anything of that sort. Things should be pretty straightforward. So in my opinion, I think this course is going to be very easy. Again, assuming you're interested, you're curious, you're going to follow along and use the information and apply it hands-on. So a little bit about myself. I am an electrical engineer. I'm an electrical engineering student. I'm right now doing my PhD at Northeastern University. And my research is in the area of space communication, specifically related to terahertz and a little bit of lasers. My goal is to make space communication faster. So be able to have satellites talk to each other faster, but also as a byproduct of that, be able to use other technologies such as like radars, for example, for sensing purposes at those frequencies. As you know, we have devices that operate in megahertz, we have gigahertz, such as like Wi-Fi and Bluetooth, and now we're trying to expand to the terahertz, which is like above 100 gigahertz. And at those frequencies, it's very high speed, so building the electronics and stuff, building the antennas and stuff, but the reward of that is with the higher frequency, you're able to get more bandwidth, and therefore you're able to get higher data rates. I also have industry experience from Northrop Grumman Aerospace Systems. I interned there twice working on satellite communications. I also worked at the NASA Kennedy Space Center and the NASA Jet Propulsion Laboratory as an intern, where I worked mainly on electronics, whether it's in the context of control systems or just building RF and analog things. And in my research right now, I am working on simulations. So again, it's very convenient that I get to teach this course, because everything that I'm about to teach you, at least the electromagnetic perspective and obviously the mechanics perspective also, is something that I have freshly learned. So I think it's going to be really cool to be able to look at it from the other lens. So let's start with a very basic question, and that is, what is a simulation? And this is really going to be the core of this course. And a simulate, if you look it up through a dictionary, you get 3 quick definitions. And simulation is just an imitation of some situation, some action of pretending or deception. Or a third definition, more applicable to us, is production of a computer model of something, especially for a purpose of study. Now, if you combine all 3, you're essentially trying to take some scenario in the real world, and you're trying to use some computer software to simulate it. And basically what that will help you do is be able to understand the situation and also be able to play around with it, move it around, and have it bash into things without actually having to go and do it in the real world, which is very nice. Now, when we think of simulations, we can really define everything that goes into simulation pretty much by variables. So what it is that we're actually trying to change along the simulation, that we're trying to see what happens when you change that specific thing. For example, if you have like an airplane going through the air, how fast that airplane is going is a variable that you could change in the simulation and observe what results accumulate as a result of that, as well as constraints that you define based on the environment, and obviously the equations that you tell the simulation, hey, based on these equations, take these variables and do stuff with them, and I'm curious what the outcome looks like. Now, simulation is generally limited by computation. So the more powerful your computer is, in other words, the more it's able to consume power, it's able to have good hardware that performs the calculations. The better your software is, the more optimized your software is, the more efficient and smooth the process is. So the simulation really is limited by your computer. And that's why simulations go hand in hand with supercomputers or clusters, because usually you have much larger processing power, much larger RAM, such that you don't really have any limitations, or you have limitations such that you still have, the simulation still takes some time to run, but not as long, because you're able to access more resources. Now, one very quick scenario or situation where we see simulations being very relevant is video games. And video games are an amazing way of looking at simulations, because you're doing exactly what we just described. You're taking something from the real world and you're inspired by that, and you're trying to replicate it in some sort of computing model. So in this case, this is one of my favorite games that I play quite a lot. It's called Rocket League, and it's basically cars playing soccer. So again, if you were to create this scenario, or if you were to simulate this, first thing you would think about is, okay, how fast is this car moving, and how fast is that ball moving? And if the ball were to go in the air, how long would it take for it to drop down? Like, for example, that's gravity equation based on the acceleration. And for example, as you see in the end, there's a collision that's taking place between the car of the main player and then the other player, as you're about to see exactly right here. So how do you define this collision, and how do you define the materials? Is the car going to break? Is it going to bounce? Is it going to, what exactly is going to take place? Another common game is very popular is FIFA, and this one's even more fancy and sophisticated because you're trying to emulate what humans are doing. So you're trying to take a human behavior. So as we can see, the player going for the penalty, and likewise there is a ball. So as the player hits the ball, you have to tell the simulation, the equation, the mechanics equations, that hey, what's going to happen upon impact when the guy's foot hits the ball, and when the goalkeeper goes for the save, and can the goalkeeper go for the save, and how is he going to fall? Now, one shortcut you can do is you can, for example, have like a real human and attach some sensors to him and have him emulate this behavior, which is what they do in this game. Or you could just build the entire thing from scratch, where you can try to design a human and see what takes place when you apply the mechanics equations. And again, you run the simulation over and over again. We also see this in something as simple as GIFs. So for example, this GIF right here is really simulating something. So the one on the left is showing you a dipole antenna. So it's basically an antenna that looks like this, and it's being fed, and the current is basically going back and forth. And what you're seeing is the charges moving along, and as a result, you see the green arrows, which is the electric field that is changing. So again, this is based on electromagnetic equations that's telling you, hey, based on the input variables, which is the movement of the charge or the current, I'm going to have a changing outcome, which is the electric field. Or in case of a receiving antenna, which is what's actually taking place here, you have the complete opposite. You have the green arrows happening first. So the electric field is being induced. The waves are traveling in the air, and they land on the antenna, and the antenna captures it. And as a result of that changing electric field, we notice that there's a current being induced. Likewise, we see on the right, this is called an antenna array. It's a little bit more of a complicated antenna, but not really. You're just basically stacking a bunch of antennas together. And again, based on the electromagnetic physics, they constructively and destructively interfere, and you're able to have some type of patterns. Now, we're going to talk about antennas later in the course, because again, that's kind of my specialty out of the things that I'm going to be talking about. That's really where I tend to have the most amount of fun. So I think I would like to talk more about antennas. Also, I think antennas are very cool just in terms of learning about electromagnetic physics in general, and wireless devices, which are like all over the place right now. So but in the case of mechanics, this still applies. So for example, as we can see here, like I was mentioning previously, if you have an airplane that's moving around and you're curious for what happens to the wing, for example, when it's going at a certain speed, one variable you can account for example, is the speed at which the airplane is going. And then based on the material you choose, based on the design, the structure, you are able to run the simulation, and the simulation will tell you, hey, based on how fast you're going and based on how much air exists, for example, how thick your atmosphere is, this is the behavior that's likely going to happen. And you can see these colors changing, just like how you can see the same thing taking place in this car. You can see these colors changing. And we're going to talk about these colors. And these colors are basically just showing you different values. So for example, in here, it could be just the force that's being applied to it. It could be the distance that is being moved by. It could be the amount of stress. So we're going to talk about how these, very often with simulations, they will look very colorful because it's a visual indication of, okay, what exactly is taking place. So if we were to take a look at this car, this could tell you, for example, again, because we don't have any information, I can only guess from this figure, but this could be the idea that this is like an impact. This is like, for example, a car that got into an accident from the front, from that right side, and that red color is probably like where most amount of force was received, and then it gets distributed throughout the rest of the car, and it bends and it breaks. So we're going to talk about that as well. So this is just another example. Okay, so now that we talked about simulation, how to define a simulation, what is ANSYS? Now, ANSYS is just a tool. It's just basically a software that we use, and it's basically the little complicated calculator that does everything for us. So once we define a scenario that we want to simulate, once we identify what variables we want to change, then we want someone to actually do the heavy lifting, and that is basically ANSYS. Now, there are similar softwares familiar to ANSYS, although this one is pretty popular because it's a multi-physics software, meaning you can simulate different kinds of physics. They have equations for different kinds of physics. You could use it for design, testing, operation, and you can tell from looking at the stock price that it's actually becoming more popular. It's growing. It's a growing company, and these companies basically make money from selling their licenses to private companies, and that's how they make their money. And because like, for example, the price is going up, you can tell that okay, this set of products are likely in demand because more people want to own a share of this company. But again, I mean, we're not going to talk about stocks today. We're talking about simulations, but this is just a good way to get you to think about, okay, is this a good software to use? And then when you go and look at the communities out there and the upgrades, they do upgrade the software quite regularly. So it's pretty good software to use. Now, before I move on to physics, does anyone have any questions so far? Okay, cool. All right. So again, based on these two figures that I showed you previously, what is mechanics? Mechanics is going to be basically a core physics that we're going to be talking about in this class. And it's basically just talking about the physics based on these mechanics equations. And basically it's very simple stuff. So when you think of mechanics, think of large things like this figure right here, like, okay, this car is being pulled. Is it balancing this weight? There's an angle, which if the tires have friction, is that slowing it down? What exactly is going on? So whenever you think of mechanics, think of large things, think of like things that like smash, move around, and break, friction. These kind of things are really what we associate with mechanics. And for example, on the right side, we have some of the more common equations that we like to think of. So basically, these are going to be the equations that are pre-installed into ANSYS whenever you choose to run some sort of mechanical simulation, whether it's like a stress analysis, like a statics problem, or like a dynamic system. And likewise, what is electromagnetics? Electromagnetics is a little bit newer than statics, and it's based on electromagnetic physics. It's based on Maxwell's equations, which the fundamental idea behind Maxwell's equations is really simple. It says, one, in order for you to have an electric field, you need a charge, meaning a charge is what causes electric field, which causes electricity to happen. Two, you cannot have a magnetic monopole, meaning that magnetism is not something that exists on its own. It has to exist as a byproduct of electricity. Hence, a magnetic field is usually the product of a changing electric field, which is what the third equation says. It says here, as the electric field curls and changes, or in this case, as the magnetic field is changing, you're inducing an electric field. And then likewise, in the Ampere-Maxwell law, it's the complete opposite. This is basically what tells us about electromagnetic induction, that it says, okay, if you have current going through a wire, that's going to give you a magnetic field. But also, if you have an electric field that is changing, that's also going to give you a magnetic field. So that kind of goes back to the second equation that's telling you, okay, if you want to have a magnetic field, you likely have to go do something with the charges because there is no such thing as a magnetic monopole, at least not as of now. Who knows? Now, I have used simulations very recently, and I'm just going to show you some quick examples. So I published 3 papers recently, all of them involving simulations, and they involve different kinds of simulations, so it's going to be very cool to look at. So in this very first paper, what I basically did, me alongside my advisor and my co-author here, we basically looked at trying to design a system of satellites in space, and we really wanted to simulate how they would communicate to each other. And the difference, the variables that I was talking about in this case, for example, would mainly include the type of frequency used, which would in correspondence determine the data rate. So basically what we go ahead and did is we define a scenario, we define a channel, and in other words, a channel is just basically like a scenario, like we say, hey, this is where things are taking place, this is Earth, this is space, this is the type of air, this is the type of molecules existing. We talk about what's likely going to happen as your waves start propagating into space. So again, we're still defining that model. We're putting the equations, preparing for the simulation. And then likewise, we're taking the satellites and replacing them in locations strategically. So again, adding more variables to the simulation. And then after some time, and these are, for example, some of the variables. And after some time, we actually run the simulation and bam, we get some results. And we say, okay, for some kind of frequency, you get this kind of data rate. And for the other kind of frequency, you get this kind of data rate. And you don't really have to worry too much about the details of what's going on here, but this is just telling you that this is how you get to think about a simulation. You first define the environment, you define the variables, you define your technology, you place your things in place, and then you click run. Now, in this case, we built this simulator in-house in my lab, but not in this case. In this case, I was designing an antenna, more of really a deployment method for an antenna. So when you launch a satellite in space, you have to put an antenna on top of it. And that antenna is basically what's going to communicate back to the Earth or to the other satellites. Now, if you want to have a large antenna, it's usually like a pain to try to deploy it mechanically. And let alone trying to steer it, like moving it around mechanically. So in this case, I come up with an idea that I say, hey, you can use motorized rods that deploy the antenna, but also based on how much you're able to change each rod, you're going to basically move the antenna around, and this is going to be really compact and nice, and it's going to save the satellite a lot of power. And the simulation that takes place in here is how does the movement of the antenna change the amount of power being propagated in a single direction? Okay, so again, this is a different kind of simulation where you're simulating an antenna moving, and based on the antenna and the movement of the antenna, you're able to see what happens to the waves. And this is also similar to this paper right here, where this is actually a dual band antenna, which is basically the exact same antenna designed. But in this case, what I'm simulating is I'm telling it, hey, instead of shooting just one beam here, what about you shoot 2 different beams at 2 different frequencies? And I want to see, based on the frequency, which now becomes the most important variable in the simulation, how directive the beam is going to be, how much power is going to be at the receiver, and also how much loss is there going to be by the time the beam leaves the cables and goes into the antenna. So this is, again, defined by the equations of, okay, what does the antenna look like? What does the electromagnetic physics look like? Which in this case, this is a different software. It's called FICO by Altair, and they do all the heavy lifting, okay? So these are just quick examples of how antennas actually, or how simulations in general are actually useful in the real world, at least based on what I have been doing. So does anyone have any questions so far? Okay, all right, cool. All right, now on to a bit more of like a philosophical discussion. Something you probably heard someone say before at some point is, do we live in a simulation? And I really like this question because this really gets you to, this is really where you get a deep understanding of what a simulation is. If you watch people like Elon Musk or Lex Friedman or Joe Rogan, you'll see a lot of times these people talk a lot about simulation theory, or this idea of, oh, do we live in a simulation? And the reality is the question of whether we live in a simulation or not is irrelevant, because again, once you understand what a simulation really is, you understand that it's just really a modern way of what we call life in this case. For example, the people who are advocates of simulation theory say, oh, do we live in a simulation? Assume that there is some type of program that is being run where you as a human are ran by some equations, and for example, how you grow and how you interact with other things, and how the universe, for example, is made of equations that are made to change and evolve and bash. And based on that interaction, it's all kind of predeterministic, or not necessarily. It could have some randomness where developer, for example, of the simulator inserts some probability equations that say, okay, some things may go this way, say some things may not go this way. And the key idea behind here is you're not really able to tell. So if you're inside the simulation, you don't really know what's outside. So if you were to think of life, for example, as a simulation, there are so many variables that could be simulated. Again, it could be like growth, your interaction, how you respond to stimuli. Like if, for example, if I were to go and hit my head against the wall, what happens? Because my hand is made of materials, organic material. The wall is made of some inorganic material, which are made of some molecules. So what happens when they interact? If you were to think we live in a simulation, this is exactly what it would basically entail. So again, if you were to simulate like electromagnetic waves coming out of an antenna, the electromagnetic waves inside the software and the antenna, although they're not conscious, obviously, they don't really tell what's outside the simulation. They don't really know what's outside the simulation. All they know is that, okay, this is like you're a wave and you're supposed to propagate in some direction based on some equations, even though you may not be aware of the equation. So again, the takeaway from this slide is, do we live in a simulation? Doesn't really matter, because it's kind of the wrong question to ask, because based on which vocabulary or angle you're looking at it, yes, we do. And for example, if you're someone who is religious, you could think of like God as the developer of the simulation, and we are living in this created life. So it's really just the old versus the modern terminology. Nothing really has changed. So going back to what I just said, keep in mind that a simulation is defined by variables, constraints, equations, and again, limited by computation, okay? So now that I talked about simulations and we kind of have a better understanding of simulations and physics, we should go ahead and check out how ANSYS works and how do you actually simulate something very simple in ANSYS. Before I go ahead and do any of that, does anybody have any questions? To have ANSYS up and running right now and copy what I'm about to say. I just want you to observe. Basically, my goal from doing this right now is everything I just told you. I want you to see how you can actually take that and transfer it into ANSYS. Okay, so when you open Workbench, first thing to the left, it tells you is, excuse me, okay, so what kind of physics do you want to play around with? Okay, so again, as you can see, there's all types of stuff going on. There's like stuff related to fluids, which is mechanical. There's stuff related to like structures, acoustics. These are all mechanical. And there's also like electrical stuff. We're going to stick with something very simple. We're going to choose a static structural. Okay, so static meaning non-moving. Dynamic means it's moving. So a static structure means like some mechanical structure that is just sitting there. It's not moving. That's kind of an easy case. So you hold it, you select it, hold it, and then you drag it to this green box. Okay, so it's going to become a standalone system. Okay, so now that we defined the physics that we want to deal with, static structural, what we basically told ANSYS is, hey, do you remember those mechanics equations I showed you from a few slides ago? We want to use these, okay? And we want to use more advanced versions of them that tells us things about like stress and strain, whatnot, based on what it is that we request from the simulation. Now, once you define what kind of physics playground you want to play in, you next go to the actual engineering data, which is essentially like the type of materials you want to play with, the type of objects you want to actually simulate. Now, in this case, like this is just showing you like a general material. You can choose like steel, you can choose like wood, you can choose like iron, you can change like play around with the temperature, you can play around with some of the equations. For example, this density will change how the material behaves, and that obviously will change whether it's going to, like, for example, bend or if it's going to crack, or things of that source. And then you can go here to this engineering data resources and look at some of the built-in materials, or you can actually upload your own material into ANSYS using these equations. So we're just going to exit out of that. We're just going to use the default, whatever it has, which I believe is like stainless steel. And then next, we're going to go define the geometry. Okay, so again, tracking back, first we told it what physics we're interested in this case, mechanics, statics. Then we told it, hey, we're going to stick with whatever default material you have, which again, likely some type of steel. Now we're going to actually go and do CAD, which I'm guessing you guys are all very excited about, because this is where you actually get to design the mechanical structure that you want to simulate. Okay, so once you click on that, it takes you to this CAD workspace. Now, this is not the best. It's cool. It gets the work done. It's kind of slow unless your computer is really, really good. But if you were to want to get better at CAD, like primarily, and you don't really care about simulating what happens to to the extent to how much power exists here. You can use something like SolidWorks or Creo or like AutoCAD. But like I think that's like more suited for 2D things. Okay, great. You do have Workbench. So I'm just going to create something that's very simple. I'm going to click on plain view so I can draw things more easily. And I'm just going to make like a very simple box. So I'm just going to choose rectangle and I'm going to make it like very small, like 4 millimeters by 4 millimeters. And then I'm going to end my sketch. And now I have this nice little rectangle. So I'm going to zoom in on it and then I'm going to extrude it. Now I'm just going to choose like some random value, like, okay, sure, 1.23 millimeter. Now I basically added some thickness to it and now it's a box. It's no longer just a planar 2D shape. Okay. And I'm going to save it. So I can either go here and click save, or I can do Control S in this case. And once I save it, I'm just going to call it design 1. Sure. Okay. All right. So going back to the workbench, I'm just going to leave that open. So again, tracking back, we started with what physics we were interested in. We then said, okay, what kind of material or structure, what kind of behavior we want our physics to emulate based on, for example, in this case, the material. And then third, what kind of geometry, what kind of structure design are we actually interested in? Now that we've done these things, we're going to actually go ahead and try to simulate the thing. So we're going to go and click on the model. And again, I think this might take some time. So usually takes about like 10 seconds. And basically what this is going to allow me to do is I'm going to go from steps 4 through 7 in that same model window where I'm going to tell it, hey, this is the type of simulation I'm interested in. Hey, these are the variables I want you to take account for. And hey, these are the outputs that I'm interested in. Show me. Okay. So we're going to wait for it to load up. And again, showed up. This is our little rectangular extruded shape that we just came up with. Again, this geometry is showing you, hey, this is what you created. Materials, again, structural steel. This is the default one that was given to me based on the engineering data initially. Coordinate system, I don't really care about that. I'm just going to stick to this XYZ plane that was given to me. Now, next is a mesh. And a mesh here really is where like the simulation can be. Think of a mesh as the variable of accuracy for how accurate your simulation is. So what the mesh does is it takes your little structure and breaks it into little components, breaks it into like discrete components, such that the simulation is able to run the math on each one of these discrete components. So obviously, if I were to take this big chunk of whatever it is and run some type of equations on it, it's not going to be very accurate because there's the shape changes, whether you're going from like the top or the bottom or whatnot. So then when we go ahead and click the mesh and we insert, or I think we can just generate mesh right here and just get the default one. We don't need anything fancy. We're going to notice that what ANSYS went ahead and did is it broke that little shape into boxes or little squares. And basically what's going to happen is based on how small or large your squares are, the simulation will tell you the values for that specific square. So now if you want something that is more accurate, you're going to make your squares as small as possible. And if you don't really care, you want something that just gives you like an approximation, you're going to go for a larger square. Now, can someone tell me why you, since obviously it sounds really nice to just go make your squares as small as possible and get very accurate results, does someone know what the downside to that is?
Takes more computational power the more detail you want to do.
Right, exactly. So because I am making my squares smaller and I'm basically making my simulator do more math, I'm basically requiring more computational power. So if you have like a computer that's like old and does not have a lot of resources, and you don't really care that much about the accuracy, you want something that's like, you want to just get like a magnitude or like a ballpark, you should make your meshes really big. And on the other hand, if you have access to like, let's say a supercomputer and you really care about precise results and accurate results, and you're able to make the meshes really, really small, by all means, go for it. So there's always going to be that trade-off between computation and accuracy. And this is going to be common in all simulations. So whatever simulation you decide to run, computation will always be in the back of your head. Okay. So, all right, now that we have created the mesh, we actually want to tell it what we're interested in. So again, because this is a mechanical structure and it's static, it's not moving, what we are interested in is we're curious, how likely is this thing to, like, let's say bend or break or I don't know, gets like pushed inside. If like, let's say if I were to fix it against my hand right here, like let's say, let's consider that this is the structure and I have it right here. And I put it like a fixed support right here, such as like a wall. And let's say I'm pushing it inwards or I'm pulling it. I'm interested in ANSYS telling me, hey, based on how hard I push it, can you tell me what's going to happen to the material throughout all these little squares? Is it going to deform? Is it going to break? And if it does deform, for example, how much is it going to deform? For example, this shape is like 4 by 4 by 1, roughly millimeters. If I were to apply a certain amount of force to it, let's say like 50 newtons to one side, and if I were to put a wall on the other side such that it cannot move, what's going to happen to the shape? So let's go ahead and find out. So then what you go ahead and do is you can go on the analysis setting, and we can choose, first we want to choose a support. So we want to, again, fix one side such that it's not allowed to move around because of this static structure. And we're going to, for example, choose this shape right here, and we're going to click apply. Now, what this just did is I just told ANSYS, hey, whatever happens, this side cannot move. It's as if this is like there's a wall against it, okay, has a fixed support. So then we can go to the other side and we can say, hey, here, we're actually interested in applying a force. Okay, so we're going to apply force to this side. And so we have a fixed support over here. We have a force over here. So now what I want to tell it is I want to go ahead and run the simulation where this is stuck in place. This is being like pushed or pulled depending on like the direction it's going in. And I'm going to give it some power. I'm going to, or some force. I'm going to give it like, for example, something very, I don't know, like 15 newtons, nothing too bad. Okay. And it's going to be going in that direction. Okay. And we're going to be curious what actually happens once to my whole structure. Again, remember, because my meshes are all over the place. So what I'm actually solving for is now that I defined a fixed support, now that I defined a force, I'm basically telling ANSYS, tell me for each one of these meshes, what's going to happen in terms of what's going to happen to the material. Okay. So then this takes us to the last step. And that is basically to tell it what we're interested in. In this case, let's say I'm interested in deformation. I'm interested in like how the shape is going to change. And then I'm going to click solve. And I'm going to wait for it to run for a little bit. And this should be very quick, again, because we chose a very small structure and we applied very little force, and bam, there's our results. So again, these colors that we saw earlier from the slides, and what these colors again are showing you. So here the unit is in meters. This is telling you that based on where you are in the shape, based on the force that was applied, how much deformation actually took place for the shape. Now, obviously, because this is closest to the support, very little took place here. And because this is closest to the force, most of the change took place in here. This kind of reminds you of what we saw with the car example earlier, right? Like if a car were to have impact head on, the very front will experience most of the deformation. The rear end is not going to experience anything. It's probably just going to absorb most of it. And again, this is just one example of like a type of simulation that we're able to run. And based on that, you can, I believe you can increase, like you're able to get more resolution. You're able to go ahead and change things. You're able to like go and create other types of solutions, for example, based on whatever it is you're interested in. And then you have to basically rerun the simulation and it's going to tell you. So again, going back to that workbench, the thought process was we first defined what physics we're interested in this case, mechanics, statics, things that do not move. We then went ahead and we chose the kind of material, for example, in this case, steel. And then we went ahead and we designed something with that steel. We made a box made of steel. And then in the actual model, we went and told it, okay, this is what we would like to happen. We gave a scenario that, again, based on the physics that's pretty defined, we were curious about what was going to take place. And then we click solve, and then bam, this was the result of what, well, this was the result, okay? So this is pretty much everything I wanted to cover today. We're gonna finish a little early because I don't want you to get too overwhelmed. But now that we've gone over what is the simulation, what is mechanics, what is electromagnetics, what is ANSYS, how do you use ANSYS, and how do you actually interpret what it is that you use from ANSYS, does anyone have any questions? Now is a great time to ask questions.